Hi everyone, in this video we will continue working on Go testing package and library, and we will look into the benchmark testing and profiling. So if you're following this tutorial, in the previous video we were just talking about the functional testing in Golang, and we just learned how to look into different way of writing, different way of executing tests and seeing the result and looking at the coverage and a lot of other things. So in this video we will continue from a different perspective and look into the benchmarking, profiling, and find out what are the issues in our test or in our code base and how we can just improve it based on the memory, CPU, and everything else. So let's dive in and look into that one. I'm just going to work on a previous project, and I will put the link to the code base in the description section, and you can just look into that one. But here I've just created a unique ID. So if you have watched my previous videos, I've used like a comparison between like a UUID and KSUID. So here we have two functions, and we have like a just normal UUID and KSUID, so it's a sortable one, this one, and we're just generating them. And also in a Go mod we have UUID and KSUID. So if you want to go and get them, basically it's very simple. All you have to do is go get github.com, Google UUID, go get, and then github.com segmentio and or segmentio/KSUID. Okay, now that we have all of these things, we're going to write some benchmark tests. I'm going to create a file. So here would be pretty much the same thing. So let's just here go to cd unique ID, and from here I'm going to create a file called unique ID underscore test.go. So we have this file, like always, because here we have the package UUID. Let's just use the same thing, and we're going to write our test. Pretty much it will be the same thing with a little bit of difference. So if you remember with that one, we would start with the normal testing, we would start with test. So here we're going to start with benchmark, and the function we're going to test is basically UUID generator. So I'm going to just copy the name, and instead of xxx I'm going to put this one, and here instead of testing.t, because we are doing benchmark testing, we're going to use a pointer to testing.b. And the same thing we need would be for basically KSUID generator. So let's just paste them here. I'm going to paste it here. Cool. So now that we have both functions, let's see what can we do. So if you're going to prepare something, then we can prepare. For example, here I'm going to just say b.log. So let's just log something. We are testing UUID generator by Google. Yeah. And the next thing that we want to do is we want to just run our test. And just pretty much when you're going to write benchmark tests, you're going to follow this pattern. There will be a for loop. So we have a for loop. Our for loop is pretty much simple. So it's I from 0 and then I less than b.n. N is the magical number here. So this is the number that benchmark test is going to give us. So how many times it could run the test. So this is always the same thing. And here that's what we're going to do. So we're going to run our UUID generator. So I'm going to just grab this one, basically paste it here. That's what we want to do. Obviously return a string, but I don't care at this stage because I want to see what can we do from here. Okay, so we are returning a string, and we will continue with that. Do we need this one? Pretty much no, so I'm not bothered with this one. And the same thing will be for benchmark KSUID. Before doing that, if we are preparing a lot of stuff, we don't want to put this. For example, if we are assigning a variable, whatever is the variable, we don't want to just put this one in our benchmark test, because that's not part of the test. The actual test is inside the for loop. So we have something called b.start timer, And also, if we are doing a bunch of things after this one, we don't want to include those things in our benchmark. So, and we can just do exactly the same thing. B dot, here, I'll say B dot stop timer. So in this case, to be honest, we don't need any of them, because let's say if you don't have any logging or if you don't have anything, this is pretty much the for loop and the benchmark test, so the subject under the test. So we don't need it. But if we have allocations, if we have to do these things, so we might need to have b dot start time. B is coming from testing.b or benchmark, and stop timer is the same thing as well. So if we are, for example, we want to log something, we want to do extra stuff. Do we need it? No, but just good to know that we have them if you want to do some whatever you want to do, log something or not. Okay, I'll keep these ones, and pretty much the same thing is going to happen. So I'm gonna just remove this space actually, because we don't need them. And here, so I'm gonna copy the same thing, and here we're going to use actually KSUID generator, and here we're doing testing KSUID. Okay, so here we have everything, and now we have these two tests. We're going to run them very simply. So if I go literally to cd, well, if I do this one to begin with, go test, and let's run everything in our package. It actually couldn't find any test, because these are benchmark tests. It's not going to find them by default. So what we have to do is to say go test dash bench and look in the current directory. So you can see, there we go. So here, well, it's just logging some stuff, and it's going to give us some result for the benchmark UUID generator. You can see we could run over like, is actually, yes, over like 3 million operations, and every operation took around 386 nanoseconds per operation. So this is the output. I'm literally going to stop this one because it makes a lot of noises. We don't need the log. I'm going to clear and run one more time. Now we're going to get a different result. Okay, it's much easier to read. So with the with the UUID, we get like pretty much over 3 millions, and it took like around 392 nanoseconds per operations. With KSUID, we got 1.8 millions, I think. Yes, around 2 millions, and all of them took 656 nanoseconds. So out of the box, you can easily see which one is slower. For example, this one took almost two times longer to compare with UUID. But here, like, it runs everything in 1 second, so we don't really see it. If you just want to see it like with lots of traffic, we don't see much. What I want to do, I want to run all of them, but here for 10 seconds. So with a bench time 10s, you're just saying I want to run the test for 10 seconds. It's just bench, I forgot the H, and if I want to run it for longer or shorter time, I can do it. So I'm gonna just pass this one. It will take a few seconds, basically 10 seconds for the UUID and 10 seconds for KSUID to give us some results. But here it will run quite a lot more, and we will see more result. So let's just wait for the result and see what do we get here. So after 10 seconds, we get the UUID generator. The number is almost the same thing, so 392 nanoseconds, 386, so it's very close. And you can see after 10 seconds, well, the whole test took 25 seconds, previously took 3 seconds. So here we're talking about the second part, which is here. So with the UUID, it took 386 nanoseconds per operation, and it could run, let me just do this one and then these three. So we had 31 million operations, in 10 seconds. With the KSUID, we only had 17 millions or almost 18 millions, and it took 663 operations per second. So now we are seeing what is actually happening and why some of them are slower, some of them are faster. But here is just really going to just do the benchmark. We don't want to talk which one is better, which one is worse. In terms of performance and benchmarking, we can see, but they have different use cases and it's totally a different decision. But here, this is just how to run benchmark for these two tests. Okay, I want to do one more thing here. So I'm going to clear this one. I want to see the memory allocation for these two. For example, here we are not really allocating any memory. So as you can see, there is no memory allocation, but let's see what do we get. But if we go to the implementation, you can see there is memory allocation. And here also there is memory allocation in a UUID and KSUID, but let us just run them in a benchmark testing and find out how, like what data are we going to get if you want to see the memory allocation. Here I'm going to do go test bench dot, and then here I'm going to pass bench mem. With the bench mem, what we are going to get is basically a memory information about all our tests. So here you can see we have 64 bytes per operation, and there was 2 allocations. And also with the KSUID, we have 32 bytes per operation. We had 1 allocations. Maybe the implementation behind the scene, because they're just allocating something behind in a memory, is different. That's why you get 1 allocation here. We have got 2 allocations there. So in a critical applications or performance, when performance is very important, when memory is very important, or like when you're working on a very, very big set of data, these are very important, because you can see, for example, here is exactly half of the half memory allocation, and here we have 2 memory allocations. And also, yes, it might take like a little bit longer, but you can see memory is much smaller. So we get some important and interesting information in this case as well, just to remember that one. So what I want to do is basically I'm going to copy the UUID generator. So let's just copy this one and come here, and I'm going to call this the second one inline. So what do I mean by inline is basically all I want to do is just to do this bit. So I'm going to, with the inline, I'm going to do this one. I'm not actually going to return anything. So if I save it, it will what is it called? It will import the UUID. So we have we're calling the function. Here we are calling the inline one, so exactly the same thing. And also we have KSUID. I don't want to run KSUID, so all I have to do here, I can say run UUID and then bench mem. So it will only going to trigger the UUID one, so it's kind of like a regex. Again, here we're going to get the same thing, 393, we're calling a function. So this is the function one, this is the inline one. The numbers are very, very close, but you can see we're going to get the same thing. So there is no difference, because if you call the function or if you call your code base, it would be still the same thing. If you want to know more, all you have to do is to just say go help test flag. Instead of go help test, you should just go to go help test flag to get richer like documentation or help as well. So here I'm going to remove the inline one because it's not really going to do so much different. I will save it. So we only have testing and we're checking benchmark UUID generator and KSUID generator. Now we are looking into profiling and we're going to actually visualize what is happening behind the scene with the memory allocation or CPU allocation. So let's see them in action as well. The command that we have to just do is to just say go test benchmark or dash bench, and now we are going to create a profile based on memory. So it's mem profile, then dash mem profile, and we're going to give it an output. So it's mem.out, and if I press this one, it's going to run the test, and generate mem.out. So now you can see we have mem.out. This file is not, you cannot view it as you can see, but if you use Go tools, now we can just see more info in regards to this file. The command we have to do is this one. So it's Go tool. So we're going to look into profile or performance profile, pprof, and we're going to give the file name, which is mem.out. If I press this file, it's going to ask, what do you want to do? So it's O for options and H for help. So if you press help, we can see we're gonna have like quite a lot of options that we can use a command. So we can just generate, for example, call green. We can just look at all the comments and many more things. So like we can have different graphs. So we can have GIF, PNG, so just to get a visualized like information. And if you're going to use some of this visualization, all we have to do, we have to install GraphViz. So if you go to graphviz.org/download, you can see how you can install it in your system. So if you're using Ubuntu or Windows or Mac, then you need to install this application or this package first. So you can use Brew if you're using basically Mac. With the Windows, you have the executable file, so exe installer, and then in Linux you can use like the apt install if you're using Debian and other things as well. So pretty much it would be simple to install. So once you install this one, then you can, from here you can just choose, for example, in GIF, you'll press enter, it will generating the report, and that's the file profile 001.gif. And then I'm gonna just do Command C or Control C actually. But now I can see more result if I look at the GIF file. So I can get PNG, and you could see I have even more options if I look here. So it depends how you're gonna look or visualize this one or output the graph. So you can see in a PS file, PNG format, I don't know, text form, quite a lot of things. Depends how you're going to use it and what do you want to do, then you can see. Also you have like a different options if you want to just look what is happening. Depends on your expectation, but mainly I'm going to focus on the visualization. So here, so if I open the profile 001, that would be the interesting thing, and we can see quite a lot of stuff now here. So if I zoom in a little bit, let me just make this one small. Okay, it's just trying to here. Okay, it's trying to run our test. It goes and run our test. We have benchmark UUID generator, benchmark KSUID generator. So you can see like how much of memory, because if you remember, the command we run was basically looking into the memory. So now we can see how much of memory is being used by KSUID and UUID. So the left one is KSUID, the right one is UUID. And also if you want to know more and understand how to read this one better, then you can go to git.io/this URL. Basically it's a documentation in this link will take you to a documentation in a GitHub for the Go package, standard library, and it will give you, like, for example, how to read all of these things. But here you can see, for example, you only use 321 megabyte. Out of that one, 239 was for the UUID and 82 megabytes only was for KSUID. Now we can see the most expensive part of our operation. So in a UUID package, when they are going to generate string, that's what happens. So it's 52% of memory allocations from that UUID. It's happened when we are calling string. So if you look into unique ID, that's the string function where we call them for both actually, and that's what happens. So the string for both of them are actually hammering the memory, as you can see. So again, in the KSUID, the biggest part is for the string. So we can see what is actually happening. And then it will continue with the UUID. We have new UUID, which was like actually not that much, new random, because when you are going to generate one, actually a lot of things happen behind the scenes. So we have new random, and also new random UID from reader. So the bigger the box, the bigger the memory is, that, or is the most expensive part of that. And but if you follow like my previous video about UUID, you can see we have more than like, or we have different functions when you are generating UUID or KSUID, and you can find the one which actually work the best for your scenario. But here is a very good type of visualization if you're going to do the same thing for a comparison between KSUID and UUID. So we use benchmark testing in Go. We created a profile based on memory allocations and memory, and then we visualized it here as well. So let's do one more thing here by just creating a profile for CPU allocations and then actually visualize that one as well. So in order to create a CPU profile instead of mem profile, you can actually just say go test dash bench. Now instead of mem profile, you're going to pass dash CPU profile and then CPU.out. So it will run the test, create the CPU.out here on the left side. And again, what we have to do here, I'm going to just say go tool p profile CPU.out, and I'll just type help. Again, I want, for example, in this case, I can just choose any of other things, but instead of, for example, GIF, GIF, I'm going to use PNG, for example, or PDF, both would be fine. I'm going to use PNG. So it generate the PNG file. I'm going to Control C, come out. This time looking at CPU, which was this PNG file. Okay, so let's make this one smaller, and I'm going to zoom in and we can see what's happened here. So for example, with CPU profiling CPU, we're going to get different results. So it just run the test. We are going to run, for example, KSUID and UUID. So you see here is 50%, here is 49% almost. That's how much time it took, and we will just move on. So it's a generator, both of them create new, again the same thing here, create new random, almost the same thing, again new random from reader, here new random with time functions, and then read, so IO read full, etc, etc. You can see, you can get like some sort of information about what is happening when you're going to run your test. And if you really care about nanoseconds or bytes in your memory, this is the moment that you can benefit from them. So you profile them based on memory, or you profile them based on CPU or other things, mutex, file readers, and a lot of these things that I was talking in a test flag. So if I just scroll up, and you can see, so we are creating mem profile rate, mutex profile. So we did CPU profile. So you can see, you can just choose them, depends on the way that you want to like actually profile them and look into them, and then visualize them with the Go tool, and just use the pprof, so or performance profiling tool, so in a Go tool. And here is basically how you're gonna just do it. So we look into the memory, we also look into the CPU profiling, and we got some result. Next thing that I want to do is to test the SHA algorithm in the standard library, and we can see the difference there as well. So here in the SHA_test, which we're in a magical package, we are benchmarking SHA-1, SHA-256, and SHA-512. And now the start timer make more sense because we have input, and now after just allocating and putting that input, or just creating that variable, we will start our timer. That's what we want to do. That's where the performance and the profiling is very important for us. So this is, we're going to start the timer here. So we are looking at SHA-1, the same thing for SHA-256. So we just the same thing, and we start the timer. Here we're going to use SHA-256 and then some 256, and then the same thing for 512. And now if we're going to run our code again, so it's go test dash bench, and here actually no, I need to go to cd magical. Now I'm going to run this one. It's going to run the SHA-1, SHA-256 and SHA-512, and you can see how much it takes per operation. So SHA-1 took 49 nanoseconds per operation, 53 for 256 and 518 for SHA-512. And also you can see how many operations it could run. So it's around, so it's 3-digit, and here is 3-digit, so it's 24 millions for SHA-1, 22 millions for SHA-256, and only 2 millions for SHA-512 or 512. But now if we look into the memory allocation, we're going to get a different result. So here we have go test dash bench dot, and we are looking at bench mem. So we're going to run all of them and look into how many memory allocations happen. For none of them we didn't have, so we didn't have any memory allocation for any of them. So if I just go and duplicate SHA-256, and let's call it with memory allocation. So it's basically the same test, but instead of this one, I'm going to say SHA-256 is SHA-256 dot new. So we're just allocating a memory to this variable, and here I'm going to just call it sum. So it will be still the same thing. So it's SHA-256, and then we're going to use that variable to just create it. And if you just only, so I'm going to actually stop this too. Well, I'm not going to stop it, but I'm going to just comment them out. And here we're going to only run the SHA-256. So I'm going to say go bench. Instead of dot, so instead of running everything, we just want to run 256 one. So it's a regex. So with the 256 one, we have no memory allocation, and it took, for example, 53 nanoseconds per operation. We could run like 21 million. Here with the 256 with memory allocations, because we had this line here now, we actually have one memory allocation, and it just was 64 byte per operation, and it took 71 nanoseconds per operation. So instead of 21 million, here we have 16 million. So we can see the significant drop if we're going to have just a normal memory allocation. Do we need to do this new? It depends on use case, or maybe not, but you can see what is happening. In a normal scenarios, you're not going to notice it, but if we have a just like an application which is going to work with a very big set of data, or if the performance and the memory is very important, these are the small bits and bobs that is going to just impact so much on your code base and your performance. So now that we have all of these things, let's just go and create profile, or make the just create profile for the CPU and memory, and see what are we going to get. We have got the CPU and the memory. So profile 1 was the memory one, profile 2 is the CPU. So let's quickly look at the profile 1. So it's the allocation space. You can see the only test that had allocation was SHA-256 with memory allocations. If you remember, here is the only test that we had allocations. So if you remember, none of them has any allocation. The only one had allocation was SHA-256 with memory allocations. That's why when we are looking at the output of memory allocation for profiling, we're only going to get this one. And you can see, so we have 1.4 gigabyte, and the main things happen when they were doing the sum. So this is memory allocation for this one. Again, as I said, if you want to know more information about how to read this diagram or this visualized like the PNG, then you should go to this URL. This URL would be pretty much the same thing if you run it in your system as well. So now we talk about the memory allocations or memory profile. Now let's look at the CPU. So with the CPU, it will be quite easier. And if I scroll up a little bit, you can see, for example, where things are happening. So we have the magical test benchmark SHA-1, SHA-256, 256 with memory allocation, and 512. And you can see there was a runtime as well. And if you follow all of them, you can see what is happening. Actually, the heavier one, or the basically the most expensive one, could be the 512 because it took a bit longer than every other ones. And with the memory allocation in this case, it was actually a little bit faster because yes, we sacrificed, well, we had a memory, but the CPU allocation or CPU profiling, it shows it took a bit faster. So you can just follow them and just read all of them and understand what is happening. But here with the SHA-512, we can see it took the longest and also the most CPU resources when it's going to run it. So here I think we're going to give us like a rich information how we can just benefit from this profiling as well. So if you are at this stage and at this time of the video, it means you are enjoying and you are learning quite a lot of things. So please don't forget to like the video, and if you have not subscribed, it means so much to me if you can just press the subscribe button and subscribe to the channel. I'm going to put a lot of interesting videos in the channel that we could all enjoy and benefit as well. Thank you so much, and I'm going to see you in the next video.